Hello everyone, welcome to topic 3.8, representations of solutions. In this, you should be able to use particulate models or particle models for mixtures to represent interactions between the components and represent the concentration of components within a mixture or solution. Okay. So solids, liquids, and gases, or solids and liquids, exhibit all types of intermolecular forces as summarized in the particulate drawings below. So this is like illustrating the different intermolecular forces between solutions of solids and liquids. So we see the intermolecular force as these dotted lines interacting between different substances or different particles. Okay. Intermolecular forces exist between solute particles, between solvent particles, and between solute and solvent particles. Depending on the particular solute or solvent combination, these intermolecular forces may either promote or prevent the formation of a solution. The tendency to mix is strong, but if the solvent-to-solvent and solute-to-solute attractions are strong compared to the solute-solvent, a solution will not form. So if solvent-solvent and solvent-solute attractions are strong compared to solute-solvent, we do not have anything that dissolves. So that's what that means. We will look at this more in a future lesson in math, or future section, and mathematically model it as well. The term miscibility describes the ability of two substances to mix without separating. So that allows us to have homogeneous mixtures, if you remember back to your first year of chemistry. Similar materials are miscible in each other, or like dissolves like. Though do not say that on the AP test. Say something that is talking about the similarities in intermolecular forces between substances, because that is where this comes from. This is the result of similar intermolecular forces. Okay. Polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. Okay. So a solution forms if the solvent-solute interactions or attraction is greater than the others present. So solute to solute and solute to solvent. Okay, and that's summarized in this little diagram above. So when this interaction is greatest, you will see something dissolve. When it is not, and the like components are more attracted to each other, then you are going to not see it dissolve. So solution will form if the solvent-solute interactions are relatively equal to the others. However, if the solvent and solute are stronger than the other one, then a solution will not form, just to restate. Concentration can be represented in particle diagrams as well. And this is drawn by just showing relative amounts of solute dissolved in solution. The more particles, the higher the concentration, so you would then draw more. When particulate drawings are compared to one another, you calculate the ratio of individual particles to determine the concentration in the difference in concentration between them. So if we look at the example that's down here, we see a 0.2 molar potassium chloride and a 0.1 molar. And if we count, we see that we have twice as many in the A model than we do in the B model, which represents the fact that the A model, 0.2 molar, is twice as concentrated as the 0.1. Okay? So we draw half as much when it's half as concentrated. Continuing on to our I do's. So here we're going to look at which solvent would be most effective in dissolving the following solutes: hexane or water. Identify the dominant type of intermolecular forces present between the solute and solvent particles, and draw the particulate drawing showing where these interactions occur. Okay, so for ethanol, we could say that either may be effective because ethanol has a carbon chain and that exhibits similar London dispersion forces to hexane, while it also has an OH bond that can do hydrogen bonding. However, the hydrogen bonding is very strong, so it most likely would dissolve best in water. And then we are also supposed to draw particulate drawing. So here in this diagram, we would show then that there's hydrogen bonding occurring here between the opposite dipoles, and because hydrogen bonding is the strongest intermolecular force present in ethanol, it makes water most likely to be the strongest or best solvent for ethanol. Okay, now looking at potassium chloride. So we know that potassium chloride is a salt or is ionic. So this requires something with permanent dipoles to dissolve it. Water is polar and capable of hydrogen bonding and dipole interactions, so it is most likely to dissolve potassium chloride via ion-dipole interactions. Okay, so when we model this, we would show the negative end of the water molecule closest to the positive cation, which is potassium, and so it would form its hydration shell like this. And then to form chloride, the hydrogen atoms orient towards the negative anion because they have a partial positive charge from the dipole, and so that is how this hydration shell forms. Okay, now let's look at the we-dos. So here we go. Of the molecules above, which would form hydrogen bonds with water, which would form dipole attractions with water, and which would form London dispersions forces only with water. Okay, pause the video and attempt this yourself first, please. Okay, so we would see hydrogen bonding in things with OH, NH, or HF groups in them, and that is because in order to hydrogen bond, both parties have to have those types. Now you can mix and match, but it must be OH, NH, and FH to hydrogen bond, and both interactions must be that. To do dipole, that is ether ketone, and that is because those are polar groups. Okay, and so if we have, even if water is capable of hydrogen bonding, the interaction is not as strong as a true hydrogen bond, so we call it a dipole-dipole interaction. Then the alkane is capable of only London dispersion forces because it is super nonpolar, and thus only London dispersion forces are capable in it. Here, you will draw particulate models of two alkane models and show how the strongest intermolecular force acts between these. What is the name of this? Well, so we would draw our CH3 bonded to a CH2, bonded to another CH3, and then somewhere in here you would just draw, and it can be to the CH2 component as well, but for the sake of brevity, I'm not going to expand these out a lot. And then this would have a temporary negative dipole and a temporary positive. And because those are temporary, that is London dispersion forces. Okay, and because the negative and positives are here, we would have a negative on this end and the positive here, and those would be temporary as well. Okay, continuing on, draw the particulate models of two ether molecules. Draw how the strongest intermolecular force acts between the molecules. What is the name of this? So we would draw each one, And try and make sure you're drawing it bent so you can actually show the interactions. That's one of the key parts. And then we would show a dotted line here because this would be our positive dipole and oxygen is always the negative. Except with fluorine, obviously. And so we would see here a dipole-dipole interaction. Because those are permanent dipoles. Now using this, complete the UDOs, check your work, and thank you guys.